This is EEE371 Electric Machines. I am Ali Nawaz Khan and I wanted to discuss some topics regarding voltage regulation and efficiency of the transformers. As we solved the model for a transformer and created an equivalent circuit, we came to know that the real transformers, they contain series impedances. So what happens is that the transformer's output voltage would vary with load. If we vary the load at the secondary side of the transformer, then it would have an effect on the voltage, uh, output voltage of the transformer. So what we do is that we perform two tests, the no load and the full load test, and in both cases we record the output voltage of the transformer, and then the variation of this output voltage is termed as the voltage regulation. So in other words, the voltage regulation is actually equal to the voltage of the secondary at no load minus the voltage of the secondary winding at full load divided by the voltage of secondary at full load multiplied by 100%. So this gives us a value of the full load voltage regulation, and this can be further solved because the secondary voltage in case of no load, if there is no load on the transformer, then the secondary voltage is actually a function of the primary voltage divided by the turn ratio. So we replace it by Vp over A minus voltage in secondary uh, at full load divided by voltage of secondary winding at full load, and we obtain the voltage regulation. Now this is a very important quantity, and it gives a great insight to us regarding the behavior of the transformer in case of the subjected load. If the load is leading or lagging, or it is not causing any change into the power factor of the transformer, then we'll be obtaining certain values of the voltage regulation. So under the per unit system that we solved last time, VR voltage regulation would be equal to V voltage of the primary per unit minus voltage of the secondary full load calculated per unit divided by voltage of the secondary winding full load per unit multiplied by 100%. Here VSNL and VSFL are secondary no load and full load voltages. So what happened is that in case of an ideal transformer, there is not going to be any difference between the secondary voltage in case of full load and no load. But in every practical transformer, this is a real value. It would have a value, a positive or a negative value according to the loads connected to a transformer. So the voltage regulation being an important quantity, as it tells us about the behavior of the transformer, and if we want to calculate the voltage regulation of a transformer, it is necessary to understand the voltage drops within it. So what we can see is that this is an equivalent circuit of a transformer, and in this equivalent circuit we can ignore the excitation branch um, losses because they are very small, so they can be conveniently ignored. So we have actually the series resistance and the inductance to consider. The series impedance is to be considered while calculating the voltage drop across a transformer. So the VR depends on the magnitude of the impedances and the current phase angle. The the current from the primary flows towards the secondary and passes through these impedances, and obviously it is going to have an effect on the angle of the current. So a phasor diagram is often used in the VR determinations. If we are able to quantify um, the vectors of the current and the voltages at their appropriate angles, we would be able to identify the effect of voltage regulation in a transformer. The phase voltage Vs is assumed to be at 0 degrees because we consider it to be no difference between the voltage at the secondary side. It does not contain any angle, so we take it as a reference, and then all other voltages and currents are compared to it. So if we look at the diagram and apply KVL, we can see that this voltage Vp over A is actually equal to the sum of voltage in secondary plus the drop across this impedance. The drop of voltage across this impedance plus this secondary voltage is equal to the applied voltage Vp over A. So Vp over A is equal to the secondary voltage plus R equivalent and Is is flowing through it plus J X equivalent and Is is flowing through it. So by following this regime, we will be able to plot a phasor diagram of the transformer. This figure signifies the effect of having leading, lagging, or unity power factor on the voltage regulation. The phasor diagram is shown here. As we mentioned previously, that Vs is taken to be at 0 degrees. It is taken along x-axis. So the secondary voltage is along x-axis. Then there was this drop, which was R equivalent Is, that occurred in the direction of the current, since in this case it has a lagging power factor, or the current is lagging with respect to the voltage. So R equivalent Is vector would be in the direction of the current in the secondary coil. Then there is the 90-degree opposite factor introduced by the inductance X equivalent multiplied by Is. So it has a 90-degree difference than this R equivalent Is vector, and eventually we get the primary voltage Vp over A. It seems to be much longer in terms of magnitude. It is much longer than the secondary voltage. So we ended up supplying more voltage to the primary side in order to obtain a particular value of secondary voltage. So in this case, the transformer is operating at a lagging power factor, and Vp over A is greater than Vs, and it means that if we substitute it into the formula, and Vp over A minus the secondary side divided by the secondary side voltage would be a value greater than 0. It would have a higher value. Then the second scenario is when the transformer is operating at unity power factor. In case of unity power factor, both Vs and Is are in phase. They are at the same angle. So R equivalent Is vector would be in the direction of the source voltage. And then there is this 90-degree difference due to the inductance Jx equivalent Is, and eventually we can connect these 2 points to get the vector Vp over A. In this case as well, Vp over A is greater than Vs by a factor equivalent to the impedance of the series impedance of the transformer. So a transformer operating at a unity power factor, Vr is still greater than 0. It is still greater than 0 because Vp over A vector appears to be greater in magnitude in comparison to the voltage at the secondary side. And the third scenario is when we have a leading power factor. When current is leading the voltage, it means that Vs and Is are forming such angle, and in this case the R equivalent Is vector would be in the direction of the secondary current, and then there is this 90-degree difference in the direction of the vector Jx equivalent Is, and eventually if we connect the dots with another vector, Vp over A is actually smaller than Vs. In this case, if we calculate the voltage regulation, which was this minus this divided by this, it would be actually a value smaller than 0. So a transformer operating at a leading power factor, if the secondary current is leading, the secondary voltage can be higher than the referred primary voltage. VR would be less than 0. Having studied the effect of voltage regulation, we can see it depends upon the leading, lagging or unity power factor at the secondary side of the transformer. We can now calculate the efficiency of the transformer. Efficiency is equal to P out, output voltage, output power divided by the power in multiplied by 100%, and the input power is actually equal to the losses plus the output taken from the system. So this equation can be rearranged as P out divided by P out plus P losses multiplied by 100%. So this is the efficiency of the transformer, and it can be equally applied to the efficiency of other machines, which are the motors and generators. So we need to actually categorize this loss factor, and we already know that there are three types of losses in a transformer equivalent circuit. One are the I square R losses, which is due to the series resistance. Then there is the hysteresis loss, which is due to the resistor RC core, which is that's the core. Then there is the eddy current losses, which are again due to the losses in the core of the transformer. So the output power of the transformer was equal to the secondary voltage multiplied by the secondary current multiplied by cos of the theta at the secondary side. And we, by substituting these values into the equation, the efficiency parameter is equal to VSIS cos of theta divided by the power losses in the copper plus the power losses in the core plus VSIS cos of theta, which is again P output multiplied by 100%. So by following this method, we can calculate the total efficiency of the transformer. Let's solve an example now. It is the fifth example in chapter 2 of the book as well. It states that a 15 kVA, this is the power, 15 kVA, 2300 by 230 volt transformer. So this transformer is a step down transformer, and we can calculate the turn ratio as well. It would come out to be 10:1 in this case. For this particular transformer was tested by an open circuit and closed circuit test. So they performed open circuit and closed circuit test on a step down transformer uh, able to supply a rated power of 15 kVA, and the results are summarized below. The voltage in open circuit test was 2300 volts. The current in open circuit test was 0.21 amperes, and the power in case of open circuit test was 50 watts. For short circuit test, the voltage was measured to be 47 volts. Current short circuit was 6 ampere, and the power in case of short circuited arrangement was 160 watts. What they want us to do is to find the equivalent circuit of this transformer referred to the high voltage side first, and then from the low voltage side. So as we did in the classroom as well in earlier lectures, we solved the equivalent circuit from the primary side as well as from the secondary side. So they want us to repeat this process for this practical example. Then in part C, we are required to calculate the full load voltage regulation at 0.8 leading power factor and 1 power factor, unity power factor, and 0.8 leading power factor, as we saw in the phasor diagrams on the previous slides as well. Then they want us to plot the voltage regulation as load is increased from no load to full load at power factors of 0.8 lagging, 1 and 0.8 leading. And finally, what is the efficiency of the transformer with the power factor of 0.8 lagging? So we just revisited the efficiency in the previous slides. Let's proceed with the solution of this particular example. Part A required us to find the equivalent circuit of this transformer referred to the high voltage side. And if we look at this figure, it gives us the equivalent circuit. Ignore the values for the time being because these would be calculated in the subsequent slides, but the equivalent circuit is actually it comprises of this R equivalent, J equivalent, and then we have these two this excitation branch that contains the hysteresis and the eddy current losses, and the magnetization current is also flowing through JXM. So what we need to do is to calculate the excitation branch values of the equivalent circuit. Theta OC is or cos of theta open circuit is equal to power open circuit divided by voltage and the current recorded in the open circuit test. So if we take the cos inverse, the power in open circuit test was 50 watts divided by open circuit voltage was 2300 volts multiplied by 0.21 amperes of current, and it comes out to be 84 degrees. So in the excitation branch, in case of open circuit, the theta was 84 degrees. So the admittance in this case would be YE is equal to IOC divided by V open circuit, and with this angle minus 84 degrees, and it comes out to be a very small value of 0.000095 minus J 0.0000908 S. And if we take the reciprocal, we'll get the resistance, the value of the resistance in the core RC would be 1 over this very small quantity, and comes out to be a large 105 kilo ohm resistance. And X of M, the magnetization branch would have 11 kilo ohm um, resistance to offer. We next proceed to use the short circuit test data to calculate the R equivalent and JX equivalent, the total impedance in series provided to the secondary side. So theta in case of short circuit would be equal to cos inverse of power in short circuit test divided by voltage and current for short circuit test, and it comes out to be 55.4 degrees. And the equivalent series impedance in this case would be the voltage divided by the current in case of short circuit test, and with an angle theta which we have already calculated, it comes out to be 47 over 6 with an angle of 55.4 degrees. And from here we deduce that the R equivalent has a value of 4.45 ohms, while X equivalent has a value of 6.45 ohms. In part B of the example, we were required to find the equivalent circuit referred to the low voltage side, and for that we need this we need to find the values for this particular equivalent circuit model that states that AIP is flowing into the secondary side, and then there is this branch for the where it gets the current gets divided, and the remaining current flows through R equivalent at the secondary side and JX equivalent at the secondary side, and eventually we have an IS and VS from the secondary side of the transformer. So what we knew before is that we need to divide the impedance by A square. This is the relationship between the primary and the secondary side. A has a value of 10. So when we divide our original values with A square, we get 1050 as RC. RC over A square is 1050 ohm. X of M becomes J 110 ohm, and R equivalent becomes 0.0445 ohms, and X equivalent becomes 0.0645 ohms. So all we were required to do was to divide these branch values with A square, and we obtained the equivalent circuit as shown in the figure. In part C, we are going to calculate the full load voltage regulation in case of 0.8 lagging power factor, unity power factor, and 0.8 leading power factor. So for that, we need to plot a phasor diagram for all the three cases, and we need to calculate the full load current on the secondary side of the transformer. So IS rated is actually equal to the power rated divided by voltage in the secondary rated. So we know that it is designed to provide 15 kVA. So 15,000 divided by the secondary side voltage, which was 230 volts, it gives us 65.2 amperes of secondary current. This is the maximum rated current in the secondary winding. Now we have this formula that the Vp over A is actually equal to Vs plus R equivalent Is plus Jx equivalent Is. For 0.8 lagging power factor, Is would be equal to 65.2 amperes with an angle of 0.8 cos inverse, and it comes out to be minus 36.9. From this we can calculate Vp over A to be equal to the secondary Vs 230, and we do not assign any angle to the secondary voltage, plus the value of R equivalent was 0.0445 in the preceding slide, multiplied by this Is lagging current, plus the value of Jx equivalent was J.0645 multiplied by this value of lagging current, and solving it results in 234.85 at an angle of 0.40 degree volts. So the voltage regulation would be Vp over A minus Vs at full load divided by Vs full load, and it comes out to be 234.85, the magnitude minus 230 over 230, and it is 2.1% voltage regulation is noticed in this particular scenario. So we can plot it here as Vs is 230 with 0 degree angle, and then Is is 65.2 amperes with minus 36.9 degree angle, and it is shown by this lagging vector, and then we multiply the R equivalent with the Is, and it constitutes this vector. Then we have a 90-degree opposite vector constituting the inductance, and then eventually we connect these 2 points together to form Vp over A, which is 234.9 at 0.4 degree volts. Of course, this is not drawn to scale. For you can argue that this 0.4 degree angle is shown to be a very large angle in this picture, because the value of R equivalent and X equivalent is actually very small. So this is not drawn to scale, it just gives us a rough idea of how things are being calculated. Let's solve it for unity power factor. For unity power factor, the value of the rated current would be 65.2, but the angle is now 0 degrees, because there is unity power factor. It means that voltage and current are in phase, so there is no phase difference. So we'll be using Is is equal to 65.2 with a 0 degree. In this case, the Vp over A value would come out to be 232.94 at an angle of 1.04 degree volts, and the resulting voltage regulation would be 1.28%. So we can see from the phasor diagram that 230 at 0 degree volts is the secondary voltage, and the secondary current is 65.2 amperes, and when we multiply it with the resistance R equivalent and Xm equivalent, we obtained a Vp over A equal to 232.9 by 1 with an angle of 1.04 degrees. So we obtained a voltage regulation of 1.28% in case of unity power factor. Proceeding to solve this particular example in case of a leading power factor of 0.8, in this case Is would be 65.2 cos of inverse of 0.8, and it comes out to be 65.2 with a positive 36.9 degree assigned to the current amperes. Again, solving it, Vp over A is equal to Vs plus R equivalent multiplied by Is plus Jx equivalent multiplied by Is. We obtained 229.85 at an angle of 1.27 degree. These volts are obtained at the Vp over A. So the resulting voltage regulation is Vp over A minus Vs full load divided by Vs full load in terms of percentages out of 100, and it comes out to be minus 0.062%. And the corresponding phasor diagram would have 230 volts Vs. On the x-axis, the current is leading by an angle of 36.9 degrees, and then it would result in R equivalent multiplied by this Is would have a vector in the direction of the secondary current. Then there is this 90-degree phase shift for x of m, for x equivalent, and eventually we get a Vp over A is 229.8, which is slightly less in magnitude than the secondary voltage. So in this particular scenario where current is leading, we actually have lower value of the voltage applied at the primary side in comparison to the secondary voltage. Now, part D of the example was very interesting. They wanted us to change the load, the value of load current for all the three calculated instances with power factor lagging zero point 0.8, with unity power factor, and with 0.8 leading power factor. So, and calculate the value of voltage regulation in each case. So what happens is that as you increase the load current, it would be having an effect on because the load current is going to affect the value of the current Vp over A calculated through the equation. So eventually we get different values of voltage regulations. What they did was while solving the example, they used a particular MATLAB code to change the value of the load current. The load current is represented by the current drawn from the secondary coil. So we are changing the value of Is according to the different types of angles associated with 0.8 leading, lagging, or unity power factor. So they came up with this particular plot. As we increase the load current, or the value of Is, and calculate voltage regulation on each instance, the following three curves are observed. In case of lagging power factor, the voltage regulation seems to have a linearly increasing relationship with respect to the load current. As we increase the load current, the voltage regulation increases in a linear fashion. The same is observed in the case of unity power factor, but the slope of the line is less in comparison to the voltage regulation curve in case of a lagging power factor applied to the transformer. But it is still varying, increasing linearly with respect to the increase in the load current values. Uh, what's very interesting is that in case of a leading power factor situation, if you increase the load current, the voltage regulation tends to decrease linearly, but the decrease is observed to be quite less. But it is decreasing linearly. So in other words, that as you increase the value of Is, the value of Vp over A gets less and less as more and more current is drawn from the system having a leading power factor. And in case of a unity, we have a linear increase, which is actually less than the voltage regulation plot for lagging power factor. So we can, based on this available evidence, we can assume that a more lagging system would have a higher slope of the line in case of variation in the secondary or the load current drawn from the transformer, and a very high leading system would have Vp over A values less in comparison um, to the secondary voltage value. So with less voltage input, we are obtaining the same output voltage in case of highly leading power factor systems. The last part of the example required us to calculate the efficiency of the transformer for the three stated cases of power factor. For that, we need to calculate the losses, and the copper losses are I square R losses. So we can calculate it as IS square multiplied by R equivalent, and it comes out to be 189 watts. The core losses are the voltage across the primary square divided by R of C. So it comes out to be 234.85 square divided by 1050, and it is 52.5 watt. So the output of the transformer at a given power factor is VSIS cos of theta, and 230 multiplied by 65.2 ampere multiplied by cosine of 36.9 degree, it gives us 12,000 watts. So the efficiency of the transformer by putting in all of the values of P out divided by P copper plus P core plus P out multiplied by 100% comes out to be 98.03%.